Okay, so we will see the next question. Question is match list 1 with list 2. So list 1 contains ores and list 2 is the composition. So basically question from the metallurgy part. So here if we'll see the ores, we have hematite, okay, we have magnetite, calamine and collinite. So basically here we know hematite and magnetite are the ores of iron. Okay, so here hematite is nothing but basically it is Fe2O3, it is this. Okay, magnetite is another ore of iron, that is Fe3O4. Calamine is an ore of zinc, it is basically zinc carbonate, and here you will see this is zinc carbonate. If we will see the collinite part, it is nothing but the ore that contains aluminum and silicon. So here is the last one. So we can see the appropriate option, it's A3, B1, C it's 2 and D is 4. So I think it's option number 2 only. So 2 is the correct answer. Let's come to the next question. So here you are given a 10-liter flask. Okay, so this is basically from gaseous state and this is just based on the ideal behavior, you can say. So let's read out the question. A 10-liter flask contains 64 gram of oxygen at 27 degrees Celsius. So first of all, see, you are given 64 gram oxygen. Oxygen means molecular oxygen, it is O2, don't take O. Okay, and the volume given here is this. Fine, assume O2 gas is behaving ideally, so ideal behavior is preferred. So we know for ideal behavior we have PV equals to nRT. Next, the pressure inside the flask in bar is, so you are given the gas constant and you are asked the pressure. So considering the ideal behavior, we can easily apply PV equals to nRT, where P is the pressure, V is the volume of the container, N is the number of moles of gas present, R is gas constant, universal gas constant, and T is the temperature. So here you will see that pressure expression will be like nRT upon V. So this is the expression for pressure. So here let's calculate the number of moles of oxygen. We know the mass is given and we know the molar mass of oxygen, it is 64 gram per mole. So it is 32 gram per mole for oxygen, that is O2. So here given mass by molar mass, and this is going to be 64 upon 32 and that's coming out to be 2. Fine. So here we can put 2 into the value of R is already given in terms of liter bar, Kelvin inverse, mole inverse, and this is 0.0831 into temperature is 27 degrees Celsius. We have to get that in Kelvin. So in Kelvin it will be 300 Kelvin. And what is the volume? Volume is 10 liters. So on solving this expression, you will be basically getting 4.9 bar of pressure. This is quite simple. Just you have to put the values and get the answer. So this is coming to be 4.9 bar. Okay, so let's move on to the next one. For a first order reaction A to products, initial concentration of A is 0.1 molar, which becomes 0.001 molar after 5 minutes. Rate constant for the reaction in minute inverse is. So basically from chemical kinetics, that is simply from the first order part. Okay, so let's check what data we are given with. So basically we are given the initial concentration of A. So I'll be taking it as A, concentration of A naught, that represents the initial concentration, that is 0.1 molar. What is the final concentration? That means after time t, that is in 5 minutes, the concentration is reduced to 0.001 molar. Okay, fine. The time taken here is 5 minutes. So rate constant for that. So we already know the formula for the first order kinetics. It is time equals to 2.303 upon rate constant K into log of A naught upon AT. That is the expression for first order kinetics. We know the time here, and we have to get K in minute inverse. So the unit is minutes, so we don't have to change that. Keep it like that and just find the value of K. It is going to be, we'll put T here. So 2.303 upon 5 into log of, what is the value of A naught? It is 0.1. And what is the value of AT? 0.001. So when we will solve this, we'll get log of 100. The value for that is 2. So it will be 2.303 upon 5 into 2, and on solving this you will be getting 0.9212 minute inverse. So that is your answer, and the answer is option number 2. Let's move on to the next part. Next question from coordination compounds. So here we have compounds, and the question is the order of energy absorbed which is responsible for the color of complexes. So what happens according to CFT, that is crystal field theory, we have d orbitals which are not degenerate. Okay, they basically split into different different energy levels. One goes down, the energy of one gets lower and the one gets higher. So basically here for the octahedral complexes, as we can see, all are octahedral complexes having coordination number 6. So here we'll see that we have EG orbitals here, and we have T2G orbitals here. So if you'll see, the difference in energy of these orbitals is called splitting energy, and that is what makes the electron to make transitions and produce color. So here we can see the order of energy absorbed. So suppose when electron is in the T2G orbital, it will be jumping to that, okay, and this splitting depends on the type of ligand that we have. Stronger the ligand, stronger more will be the splitting, and larger will be the gap. So here just think, we know water is basically a weak field ligand, it is not a strong field ligand, whereas EN, that is ethylene diamine, is a strong field ligand. So more the strong field ligand, more will be the splitting and more energy will be absorbed while making the transition. So here we can see we have two strong field ligands. Here we have one strong field ligand, and here we have three strong field ligand. So I guess the maximum energy that will be absorbed will be in case 3, then it will be first, and then it will be second. So the answer will be C, then A, then B. So C, A, B, it is option number 3. So this will be the correct answer. So moving on to the next question, we have some reaction, okay, ozone and oxygen equilibrium. So we have a reaction where ozone and oxygen are in equilibrium. Fine. We are given, let's read out the question first. For the above reaction at 298 Kelvin, Kc is found to be 3.0 into 10 to the power minus 59. So we are given Kc. If the concentration of O2 at equilibrium, so concentration of O2 at equilibrium is this, then concentration of O3 at equilibrium, this we have to get. So since this is a reversible reaction and the equilibrium is already established, so here we can write equilibrium constant expression Kc, and that will be concentration of product to the power of the stoichiometric coefficient upon concentration of reactant to the power of its stoichiometric coefficient. So, here we have to find actually the concentration of O3, this we have to find and this is given. So, can we write that concentration of O3 square equals to Kc? I am just putting the value of Kc, that is 3.0 into 10 to the power minus 59, okay, this is Kc, and what is the value of O2 concentration? It is 0.040. So, I am writing 0.040 whole, sorry, 0.040 whole cube. So, on solving this, remember this is square. So, concentration of O3 is just going to be the under root of 3.0 into 10 to the power minus 59 into 0.040 whole cube, and when you will solve this you will get the value as 4.38 into 10 raised to the power minus 32, and this will be in the molar concentration. So, basically answer will be option number